Welcome back. This is Mr. Hassan's Maths channel. I'm answering now question number 6 from the Edexcel IGCSE Further Maths paper 4PM1-2. This is from May-June 2024. I've chosen this question for one of the questions on my end of topic worksheet on P1 Cambridge integration, and I've chosen this question because I've been looking for questions like this for my students to practice, and it was pointed out to me that this is one of those type of questions. So this question here, part A, we're told about these two curves, curve C, which is this curve over here, which has equation 1, y equals 1 over 4x, and also another curve, curve S, with the equation y equals 2x squared. All right, and for the first curve, curve C, they've told us that x is greater than 0, and for curve S, the domain is x is greater than or equal to 0. So we have this reciprocal curve and this quadratic curve in this diagram, and they told us that these two curves intersect at the point A over here. And part A of the question tells us to find the point of intersection. So that's pretty simple. We just have to basically solve these two equations for curve C, which is y equals 1 over 4x, and for curve S, which is y equals 2x squared. We have to solve these equations simultaneously. So I'm going to take the y in curve C and replace it with what y equals from curve S, in which case I'll get 2x squared equals 1 over 4x. And then rearranging this, I can multiply both sides by x. So I have 2x cubed equals 1 over 4. And then I can also divide both sides by 2, which leaves me with x cubed is equal to 1 over 8. And then I can take the cube root of 1 over 8, which gives me a half. So I can see that the x coordinate of A is equal to a half. So therefore the y coordinate of A is going to be given by, we can take the equation of the curve y equals 2x squared. I think that's the easier one. And just replace the x with a half. So we have 2 times a half squared, which is 2 times a quarter, which again is a half. So we can say the coordinates of the point A are x equals a half and y equals a half. Okay, so that's pretty simple for part A of this question. All right, so now we're going to go on to part B. So just in case I forget, this is curve S, y equals 2x squared. This is curve C, which is 1 over 4x. And this is the point A. And the point A has coordinates a half and a half, just in case we need that. So it says the finite region R, which is this shaded region here, is bounded by the curve C and the curve S and the line y equals 4. And this region is rotated around the y-axis. Rotated around the y-axis, or about the y-axis, okay, 360 degrees. And what it's going to form? It's going to form it's called a volume of revolution. Okay, a solid of revolution. Okay, and we need to find the volume of that solid that is formed. Okay, so when you have an object which is rotated around the axis, in this case the y-axis. Okay, so you have a say you have a shaded region, and it's you rotate this around the axis. Basically, it's going to come out of the page and go back into it again. Okay, so it's going to be making some sort of a three-dimensional solid shape. Okay, so it's going to make some sort of shape. So in that's the case if it goes all the way up to the axis. Right? In this case, what we're going to do is we're going to try to figure out how to take this region between those two curves and rotate it about the x-axis. Okay, so what I'm going to do is I'm going to first imagine that we take just a very tiny little small rectangle worth of this shaded region. So I've taken this little tiny slice of this shaded region, a very thin rectangle. And I'm going to see what happens when we rotate just this small rectangle around the y-axis. Okay. Now, if you were looking at this from above, looking straight down the y-axis, you would see something that looks like this. This would be the y-axis coming out of the page, coming up out of the page. And this rectangle from above, you'll see from above. Let's give it a little thickness from above as well. So you see something like this. Whoops, 1 second. You'll see something like this. Let's make it thinner. That's what we would see in front of our eyes. Okay. Now, what's going to happen is this shape is going to be rotated around this axis here. Okay, the y-axis is going to be rotated around it, and it's going to wrap all the way around. So it's going around like this. I'm looking from like a bird's eye view from above. So to make life a bit easier, let me just make it a bit neater. I'm going to use a compass to show this. So this part of it would make like a circle around the axis. Oops, 1 second. Okay, and this part of it here would trace this type of shape. Okay, so you would end up with this kind of shape with the hole in the middle. So this would be like the shaded area rotated around the y-axis. And remember, there's a bit of a thickness to it, so it's going to have some sort of thickness. If you look from the side, it will look something like this. It will look something like you have a hole in the middle. Okay, it will have a thickness, which is that thickness there, and you'll have this type of donut shape with a hole in the middle. That's what's the solid that's going to be formed when you rotate a section which doesn't quite reach the y-axis around the y-axis. You'll have a hole in the middle, which is from that section over there. Okay, so I'm just still considering this, just this thin little strip. Let's analyze this thin little strip. We have here a outer radius, and you have here an inner radius. Okay, so the outer radius, let's call it big R, and the inner radius, let's call it little r. So we could say that the area of this cross section here, which is represented by this, is going to be given by pi times the big radius squared, pi r squared. That's the area of the whole thing, minus the area of the part that's got like a hole in it, right? So minus pi times little r squared. So the area, you could say, would be pi times big R squared minus little r squared. That would be the area of this cross section. Therefore, the volume of this whole shape would be, pi times big R squared minus little r squared times however high this is. Let's call it h for now. H. Okay, so that's how you would find the volume of this type of shape here, this donut type of shape. Okay, that would be the volume. So now what we're going to do is going to relate it to the graph. Okay, the graph. So here we have like the distance between the y-axis and this point over here. That would be like the inner radius. Okay, that would be like the inner radius. Okay, let me just use a different color. Okay, so that would be like the inner radius. And then you have the distance between the y-axis and that point over here. That would be like the outer radius. So this is like our big R. Ignore this R for now. And that would be like our little r. And the thickness is just like a very small section of the y-axis, which we're going to call dy. That's the thickness of the strip. That would be this thickness of the strip. So in terms of the graph, we could say that the volume of that small little strip there, when it rotates around the y-axis, would be given by pi times, now big R squared is like the x-coordinate of the graph S. This represents the x-coordinate of the graph S. Okay. And this represents the x-coordinate of the graph C. So this would be the x-coordinate of graph S, and this is the x-coordinate of graph C. So we can say that we're going to have x s squared, which would be the big radius, minus xc squared, which would be the small radius, times h, which we said we're going to call it dy. That's the width of one tiny strip. What we want to have, or what we want to find, is the volume of the whole of this shaded region rotated around the y-axis. So what we can do is you can say we want to find the sum of. That's what the integral sign actually means. It's an S that's elongated. The sum of all of these strips between the point where y equals this value, which as we know is a half. That's the y coordinate of A, up to 4 of this expression, pi times s squared minus xc squared dy. So the outer radius, outer curve, the one that's further away from the y-axis, squared minus the x of the curve closer to the y-axis, dy. So that will give me the sum of all of these strips from there all the way from a half to a 4. Okay, so if I can take my equation, so for s we have y equals was the equation 2x squared. 2x squared, that was s. And c, so if we make x the subject of this, we'll have, or x squared the subject of this, because we need x squared. So we can say s squared is going to be equal to y over 2. And for c, we have y equals 1 over 4x. If we make x the subject of this, you have x equals 1 over 4y, just rearranging that. And we want to have xc squared, so we're going to square this. You have 1 over 4y squared, which is 16y squared, which we can write in a more friendly way as 1 over 16 times y to the power of negative 2. Okay, so now we have what we need here. So we have V, the volume is equal to, I'm going to write the pi on the outside, but please don't forget that there's a pi there. Pi between the values of half and 4 of xs squared, which we know is y over 2. Okay, it's already squared, it's x squared, minus xc squared, which is 1 over 16 y to the power of minus 2 dy. That will give us our required volume of revolution. So now what we're going to do is we're going to start integrating. Don't forget the pi. It's a very common mistake there. When we integrate this, now we're going to not write the integral sign anymore once we start integrating. Notice this is not the integral sign. This is like a square bracket. Square, you add 1 to the power, so it's y squared divided by the new power. So it's going to be, we can write this just to show the steps, a half times y squared over 2. Okay, so that will give you y squared over 4. Minus, we add 1 to the power. So you have 1 over 16 y to the power of minus 1 divided by minus 1. And now our limits go on this side. So we have 4.5. Now we're going to simplify this before we substitute. So you have pi times, and this is going to give me a quarter y squared. And this is going to give me plus, because you have a minus and a minus. We have 1 over 16y. Just write the y underneath. It's better. This y to the power of minus 1 is going to be like 1 over y. So you have 1 over 16 times 1 over y, which is 1 over 16y. The y underneath is with the 16. And we got 4 and we have a half. Again, don't forget the pi. Now we have got it in the form where we can start substituting. Let's just save some space and carry on from here. So again, please don't forget to write the pi. So you have pi times, we're going to put 4 in here, so it's going to have 1 over 4 times 4 squared plus 1 over, plus 1 over 16 times 4, and you have minus, and then we're going to have a quarter times a half squared. In fact, I should have carried on here, really. Let me carry on here. Let me just do that again. So pi, and we have a quarter times 4 squared plus 1 over 16 times 4 minus, we have a quarter times a half squared plus 1 over 16 times a half. Okay, so we put those values in. and we see what we're going to get. That's going to give me pi times, that's going to give me 4 plus 1 over 64 minus, and we have, that's going to give me 1 over 4 times 1 over 4, that's going to be 1 over 16. Okay, and that's going to be plus 1 over 8. So let's work out what that is. So we can just stick that in our calculator to see what we get. We have pi, well, we'll leave the pi, we can write that at the end, but don't forget it. 4 plus 1 over 64. Okay, minus, we have 1 over 16. Plus 1 over 8. Okay, and that gives us 245, sorry, over 64. So we have 245 over 64 pi cubed units. Say units cubed, because this is volume. So this is 245. Is it 245? Just make sure. 245, good, over 64 units cubed. So there is our answer for this question. Okay, so there's a few points that are important for us to understand here, and this formula is very important for us to use in such a situation. It will help us a lot. So you have basically pi times, if it's rotating around the y-axis, you have the outer radius, the outer curve, the one furthest away from the curve, in terms of x squared, minus the one that's closer to the y-axis, that equation in terms of x again squared, dy between the limits, and you've got your answer. If it was around the y-axis, around the x-axis, sorry, you would have here dx, and it would be y squared of the one that's higher minus y squared of the one that's lower. You'll have the equation in terms of with y the subject, in terms, it will be then in terms of x. All right, and so there you'll have your situation for that. So that's how you answer such a question. Now, other questions, if I do answer them from this particular paper, will be found in the playlist that will be over here. I'd only answer questions from this paper really if I find it's going to be useful for my A-level teaching. So I might do in the future. Other questions that deal with integration and volumes of revolution from my Cambridge collection can be found in the playlist over here. Other questions from this end of topic worksheet you can find in my playlist over here, and you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.